we present Telos, the brand new rover of UIU Mars Rover Team for the System Acceptance Review of URC 2023. Our multidisciplinary team of 28 members from diverse backgrounds has been working rigorously to develop Telos with a significant upgrade of its ancestor Maven. Constructed with 6 subteams, we have developed reliable and modular subsystems with adequate quality assurance over the last 6 months. Using last year's experience visiting the MDRS, we evaluated Telos thoroughly in competition-like environments to achieve readiness for this year's competition.
We revamped the chassis subsystem with our newly designed wheels to ensure maximum suspension and traction in the competition terrain. The wheels are completely 3D printed using a combination of flexible outer parts encircling the rigid inner honeycomb structure. We conducted rigorous tests to ensure its durability in different circumstances. Rocker bogie suspension with a rear differential bar mechanism along with a spring tensioner significantly improved the stability of Telos, ensuring space maximization. We integrated a servo-driven steering mechanism for enhanced maneuverability, allowing the rover to move sideways and pivot on a single point. To evaluate Telos for the extreme retrieval and delivery mission, we have designed multiple courses that include terrain and objects similar to what we experienced last year, such as traversing over a variety of rocks, grassy fields, sand surfaces, rocky areas, steep inclines and vertical drops. The arm of the rover is also capable of quick and easy manipulation of both heavy and light objects, like towing and lifting a 7 kg payload with rope, picking up a small object such as a screwdriver, hammer, and various shapes of rock. After experiencing challenges with our previous belt pulley mechanism, we have upgraded to an improved semi-differential wrist mechanism with a 1:3:9 gear reduction ratio. 6 degrees of freedom arm is capable of opening a drawer and inserting a cache in it. Moreover, it can perform sophisticated tasks like inserting a USB drive, handling an electrical socket, push buttons, flip switches, turning a knob, typing on a keyboard, and tightening a screw. Our enhanced end effector allows the arm to pick up objects having various geometrical shapes at micro precision, regardless of the fragility of the objects. We evaluated the arm thoroughly on a configurable lander to achieve competition readiness in the equipment servicing mission.
This year, the autonomous navigation system is redesigned with a vision-based path planning algorithm with a data-driven error offset module to improve GPS navigation using our Jetson NX custom board. We have developed an object detection algorithm and a deep learning model to clearly identify obstacles and traverse most off-road terrains without getting stuck using our input from Z2i cloud points. Telos makes strategic path planning decisions to traverse to Aruko markers and nimbles to Aruko gates with our customized Aruko tag detection model specializing in detecting markers from more than 20 meters distance. On reaching a GPS location, the model takes over as the rover moves in a circular motion. On detection of a marker, it moves to a 3 meters vicinity to complete the navigation. We have also developed an informative dashboard to display real-time updates on our journey.
In addition, we developed Icarus, an autonomous multi-copter unmanned aerial vehicle to accompany the Telos on the autonomous mission. It is capable of landing on various surfaces. Besides GPS navigation, it can also detect Aruko tag from a 15-meter distance and can create a strategic path to the target location.
We have implemented a modular circuit design allowing fast swapping of faulty components. We developed a lithium-ion battery pack to provide an operational time frame of 2 hours. Our internal system monitoring unit and hybrid cooling mechanism ensure optimal internal temperature. A kill switch has been implemented for the emergency stop of the rover. To achieve real-time data transmission, we use a 1.4 GHz directional and omnidirectional antenna on the base station to communicate up to 2.5 kilometers with the rover.
This year, for the scientific exploration subsystem, we evaluated amino acids, lipids, carbohydrates, and chlorophyll to classify the soil samples into 3 classes: extant, extinct, and no presence of life. Our 3 degree of freedom subsystem can collect and evaluate up to 4 soil samples. Learning from past experiences, we prevented cross-contamination by adding a linear funnel motion toward the sample storage. Qualitative color changes are streamed back to the base station as the input to our multiple biomolecule detection-based algorithm. USB microscope feedback and microvolatile organic compound sensors are utilized to detect an extant rock sample. We also developed a pipeline of binary classifiers to classify the rock sample into igneous and fossilized classes. Our newly built custom Raman spectrometer provides us with the spectral analysis of collected samples. Several mock tests have been conducted to validate the efficiency of our developed algorithm and subsystem robustness. We evaluated Telos in various competition-like environments to ensure solid preparation of the controllers and system-level fault testing. With our thorough preparation, we are confident in our ability to perform well and achieve success in the competition. Our branding team is working relentlessly to inspire the next Mars generation of Bangladesh through multiple workshops. We are also launching a gaming application where users can add components with their own creativity to play with our rover. Best wishes to all the participating team and hope to see you all in Hanksville this summer.